Good afternoon, everybody. My name is Vimal. I work at Infocusp as an MLE, and today the topic of discussion is going to be speculative decoding. Now, all of us have been using large language models, whether it be ChatGPT or Claude or Gemini, extensively, especially in the last 6 months. Now, these models are highly accurate when it comes to generating data, question answering, and similar tasks. But there is one place where they all lag is when it comes to providing high speed inferences. So, in this talk, we will see how to improve upon that. Now, a quick show of hand, how many of you know the transformer architecture? Okay. So, what we will do is we'll do a very brief introduction to transformers. So what really is transformers? So it is the core architecture which forms the backbone of these large language models. It is a type of architecture and we will look into it. So transformer architectures are great. Now how they are built is you have an encoder which encodes the input data. Then you have a decoder which generates the output based on the encoded input, and these two are connected together. So how it really works is that you prompt your encoder with an input. Let's say I ask my encoder to generate a quote, and the decoder gives the following output, which is the only easy day was yesterday. Now, one thing to note is that when models are under training, they behave differently as compared to when they are under inference. So inference means prediction. So when you are training a model, what you really do is that you have some inputs and you have a known output. You make a forward pass of the model, you calculate a predicted output, you take the difference of the actual output and the predicted output, and then you make a backward pass to update the weights based on the loss. So every time you are doing this, you are making two passes of the model. One is forward, the other is backward. But when we are doing inference, we are only moving in one direction, that is from input to output. So here's a brief of how transformers work when doing an inference. So firstly, you start at the encoder. Uh, so again, you hit the encoder with a prompt, let's say, which is the same one as previously, generate a quote. Now you have a tokenizer. The objective of the tokenizer is to split the input text into tokens. Now, to really simplify what tokens are, so a language model understands a language, and that language is made up of a vocabulary of words. Now these words may be correct English words, or they may be some broken up representations that the model understand. For example, in this case, if you see gene and generate is broken into gene and rate. So that is how the model understands these words. So these are from a large dictionary or vocabulary that the model understands. So the tokenizer's job is to break this input into understandable words. Then we have an embedding layer. As we all know that computers and models, they don't really understand text. What they understand is numbers. So an embedding layer's job is to take each of these tokens and convert them into their corresponding numerical representations. Then comes the meat and potatoes of the transformer architecture, which is the attention mechanism. We won't go into what the attention mechanism is, but this is where all your computation regarding to how these tokens interrelate to each other, what are their dependencies and what their meanings are captured within this block. So then the output of the attention mechanism is the encoder hidden states. Now this is the output of encoder, and just a reminder that this output gets cached. Now we'll see where that caching comes into picture. Now once you have encoded your input, you move on to the decoder. So what the decoder takes, you have your encoder hidden states, which were the output of the encoder. Then what you do is in order to start generation from your decoder, you nudge it with an input token, which is a special token which it recognizes as the start of decoding. So it could be something like this, which is a start token. Now you pass this token again through an embedding because we need a numerical representation. Then you take the embedding of the start token and the output of the encoder hidden states, and you pass them through another attention mechanism, but this time this is on the decoder end. This gives you a decoder hidden state, which we then pass through a regular multi-layered perceptron layer with softmax activations. And what we really get is the probability distribution of all the tokens in the vocabulary given this input. And then from that probability distribution, we sample the most likely token. So there are different methods to sample. In this case, we are going simply with the max sampling. So whichever token has the highest probability given this input, we will predict that token as our output. Now, in this entire flow, from starting to beginning, we have only generated one output token. Now we want to generate the second output token. How does that happen? I take the output of the first step, then I feed it as an input to the second step along with the previous inputs. That will again generate another hidden state, and that will give me another probability distribution. From that probability distribution, I'll again sample my second token. Now, one thing to note is every time it generates, so this time it generated a second token, but it also generates the first token. So it will generate for all inputs that it is getting, it will generate a corresponding output token and probability distributions. So for example, if you are giving it n inputs, it will generate n outputs, where the actual output is the nth token and all n minus 1 outputs are basically the hidden outputs. So we continue this until we reach the last token. So just as we have the start token, which is a special indicator that now we need to start decoding, we also have a special token E in this case, which means to stop decoding. And we generate these hidden outputs as well along with our token at a given step. So let's just summarize what is really happening at the decoder. So in the first step, I gave it an input of starting token, and it gave me a probability distribution, which is P of X given input S. So this is a conditional probability distribution. At the second step, I gave it inputs S and and it gave me two probability distributions. One is the probability distribution of the first token. The second is the probability distribution of the first token and the probability distribution of the second token. That is, probability given input is just the starting token, and then probability given the input is starting token and the. Similarly, in third step, you will get probability, the conditional probability given input S, conditional probability given input S and the, and probability given conditional input S, the, and only. So we keep going until we get the end token. Now, there are some key takeaways from this. First is that a decoder will take 0 to n minus 1 inputs. It will generate probability distribution for the nth token. That means you take n minus 1 inputs and you generate nth output. And it will also generate 1 to n minus 1 hidden states, right? And each output is not actually a token, but it is the probability distribution of all tokens given that particular input. Now, the important part here is that the decoder will generate output one token at a time. You cannot expect it to generate multiple tokens given just one input. So this is the auto-regressive behavior of the transformer architecture. Okay, so now what is really happening is, because of all this, we know that LLMs, they take too long to generate outputs. I mean, sure, if you try ChatGPT now versus if you had tried it maybe 6 months back, so it used to take a lot of time to generate larger outputs. And if you take any open source model and you try to run it locally, then it will also take a long time to generate these outputs. Now, if we compare this in terms with a traditional software API, so when you hit Google with a query, you expect it to return responses in less than a second. Otherwise, it's considered really bad for user experiences. However, with LLMs, given their accuracy, we are ready to sacrifice that kind of response times. But that does not mean we can improve it. Now, one of the questions is, why is inference speed a bottleneck for the LLM? The short answer is matrix multiplication, but then someone might say that GPUs are pretty good at doing matrix multiplications. So how can they be slow? Well, it's not really the matrix multiplication operation itself that is slow, but when you operate on a GPU, in order to perform an operation on it, you have to transfer memory from your main memory to the GPU block. And this increases the memory overhead because the memory bandwidth is limited. So now when you do more matrix multiplications, that means you have to do more memory transfers, and that results to a slower performance. So how can we speed this up? So there are many discussions around this particular area. One of the discussions is to quantize the model. Now we all know that Microsoft had released this paper on 1-bit LLM. So the idea is that if the weights, all parameters of my model are just 1 bit in size, then that would drastically reduce the size of the model, hence reducing the amount of memory that needs to be swapped between the main memory and the GPU in order to speed it up. Then there are other approaches which talk about updating the model architecture itself. So now research shows that the encoder, I can have a very large encoder, but I can have a smaller decoder. So let's say in a 7 billion parameter model, I can have an encoder of with 3.5 billion parameter, and maybe I can have a smaller decoder instead of having a 3.5 billion decoder, because the encoder is the main sort of retainer of information. So you can replace dense encoders with dense decoders with shallow decoders. Uh, Google released a blog in 2020 where they said that in their Google Translate application, they had actually moved away from an attention-based decoder to using an RNN-based decoder. So this also is another way to speed up. Some more advanced techniques are adaptive computation related techniques. So in adaptive computation, the basic idea is that you don't compute all the layers of your model. So either by having some kind of an input which indicates which layers have to be skipped, as in case with the ADA tape, you can basically just skip certain layers while performing inference. So that also helps in speeding up. However, all of these approaches that I talked about, they require you to either update your model architecture or fine tune it or retrain it. The main question is, can I just take a model out of box and increase its inference speed? The idea is, if today I can go to Hugging Face and download any large model, can I make it fast enough? Turns out to be the answer is yes. And how we achieve this is through speculative decoding. Now, before we get into the speculative decoding as a whole, let me establish a fact. So the fact is that some output tokens are easier to generate than the others. And also, if you have any doubt, just raise your hand and ask me, because I know maybe we are going a little bit fast. Okay, so the fact states that some output tokens are easier to generate than the others, and I will prove this to you. Let's start with a very simple example. We give our model a prompt, which is generate a simple fact. It gives us an output: the earth revolves around the sun. How many of you believe that this is true? I think no one in the online audience believes that it's true. Okay, everyone believes that this is a true fact. So indeed it's a true fact. Okay, so if I break it down, what is really happening is that the encoder gets this input, which is generate a simple fact, and then the decoder starts decoding to one token at a time. Now the first token that it generates is the. Now no matter how good of a model that you use, whether it's a small model or a large model, most models will know that any factual statement will start with an article. It could be a, it could be an, it could be the, right? And in this case, it starts with a the. So this makes it an easier token to predict because the understanding of language for generating this token is very simple for both a small model and a large model. However, the next token, which is Earth, may not be as simple to predict for a smaller model. So for example, a small model may predict the man. It may not predict the Earth, right? So this makes it a complicated token to predict. Similarly, revolves is another token which is difficult to predict because Earth, which is the predecessor, which is the token that was predicted first, is a noun, and that noun can only have two kind of actions that it can do. It can either rotate or it can revolve. A small model which does not have this kind of understanding might predict dances, which is incorrect. So that makes it a difficult token to produce. However, the model around is actually a simple model, simple token to predict, because we know that revolution is a action that will take place around something, right? You cannot revolve under something. So just by how the language is constructed, some tokens are easy to predict, some tokens are difficult to predict. Similarly, after around we have the, that means if something is revolving around something, then we would be addressing that something, and nouns are addressed with an article. So again, this is an easier token to predict. And then we have sun. Now, if your model is trained well, whether it be small or large, it would know that the earth revolves around the sun. If it is a very like a very bad model, it would predict moon. But in this case, so it's kind of a equally challenging token. So this proves my point, and this also proves this lemma, which is that some output tokens are easier to generate than the others. Now, if I take a small model, let's say 7 billion in parameter size, and I give it this output, give it this prompt, generate a simple fact, then it generates this fact, which is the earth dances around the moon. Of course, this is incorrect because first of all, the earth does not dances, and it will never dance around the moon. If I give it to a larger model, which is let's say 40 billion parameters in size, it will predict the earth revolves around the sun. Now this is an entirely true statement. If we look at the union of if we look at the intersecting tokens, you will see that even the small model is able to predict 4 out of the 6 tokens correctly. We will be using this fact to design the speculative decoding algorithm. Now, how does speculative decoding work? So what we do is that we start with a small model. Let's call it MQ in this case. And we ask this small model to generate some lambda number of tokens. In this case, lambda is 3. So the small model will generate 3 tokens, the earth revolves. So it generated these 3 tokens regressively. Now we have 3 tokens, which is, now we have lambda number of tokens. Now what I will do is that I will generate a lambda plus first token. How I will generate this is that I will take the same prompt, I will take a larger model, and I will take these outputs of the smaller model as the input of the larger model. Is this clear? Anybody has any problems with up until now? Right. So the prompt gets passed to the encoder, and these tokens that are generated by the small model, they are passed to the decoder, right? So if you recall, when we were talking about how decoding works, is that you take your output tokens, you pass it as an input. So I can actually pass as many output tokens as I want to the decoder. Obviously, it has to be lesser than the token limit of the decoder itself. So now, given these inputs to the large model, it will generate the lambda plus first token, which in this case is around. So, but as I said previously, it doesn't just generate the last output token. It also generates these intermediate outputs, right, which are the hidden state outputs. So it will also generate the earth and revolves. Now, again, as I said the point, for 0 to n minus 1 inputs, the decoder provides 1 to n minus 1 hidden states and the nth output. Keeping this fact in mind, I can use these intermediate outputs that are provided by the larger model to validate the outputs of the smaller model. So the point is, if the larger model says that around before around you should have revolves, and the smaller model also says that it's revolves, that means this is correct. So this is the general idea of speculative decoding. Now, how does it really help us to speed up? Okay. Now to discuss whether this approach actually saves us time or not so we'll now take a look at that. Now let's say if the larger model had to predict these three tokens, that is the earth revolves. So what it would do is that it would do an entire run of the decoder and it will generate then it would do another run of the decoder, it would generate earth, then it would do another run of the decoder and generate revolves. So this is traditional decoding. You would take 3 runs of the larger model to generate 3 tokens. Now in this case, what we are doing is we are generating the from the smaller model, we are generating earth from the smaller model, we are generating revolves from the smaller model, and then we are just doing one run of the larger model, firstly to validate all the outputs of the smaller model and also generate the 4th token. So in the time that it takes the larger model to generate maybe say 2 tokens, we are generating 4 tokens in total. So this is a definitely win in terms of speed. Now the question that really we have to ask is, okay, this is all fine, we see that this increases speed, but how does it really validate the small model? And we are going to talk a little bit of math now, and I know that a lot of people get scared because of math, but don't worry, I will hold your hand through it. So let's start with some very basics. So when we give the model a prefix, which is some input, right, a text input, and we are giving the same input to both the models, the smaller model will generate a conditional probability distribution q of x. For simplicity, we'll call it q of x. And this is what that probability distribution looks like. Similarly, the larger model will also generate a probability distribution given the same input, and that probability distribution would look something like this. Now if you see, the distribution that is generated by the smaller model is rather smooth and rather uniform as compared to the distribution by the larger model, which has a very definitive peak. The reason why this happens is that the smaller model is not good at learning which tokens to maximize in terms of likelihood as compared to the larger model. So what this really means is that the larger model is very confident when it says that this is the right token, as compared to the smaller model, which is not as confident as predicting which the right token will be. So if we really look at the areas of interest in both the models, these are these 2 areas. So the red shaded area for both QX and PX, they denote the areas from which my token, whether I predicted using the large model or I predicted using the small model, will be predicted from, because these are the areas of maximum probabilities, right? So if I take a token from P of X, it would be coming from this red area, and if I take it from Q of X, it would be coming from this area. If I superimpose both of these distributions, we see that they have some merging. Now they exactly overlap in, if you can see my laser pointer, you can't see it, anyways the online folks won't be able to see it. So if you look at the shaded area, if I sample my token from this shaded area, then what it means is that I am sampling something which is going to have a high probability in P, and it will also have a high probability in Q. That means both the small model and the large model are saying that are both of them are confident about sampling this token. So that means that this is the area from which I should sample my token. Now mathematically, what this means is that the probability of the sample token. So of course, if you are sampling the max token from both the distributions, you will be considering the max probability given by both of these distributions. So if the distribution of if the probability given by the small model divided by the probability given by the larger model is less than or equal to 1, that means that that token is correct, right? Why does this work? If a token is assigned a higher probability by the larger model as compared to the one that is assigned by the smaller model, then by default it means that the larger model says that this is the correct token, right? Okay, anybody has any doubt in this? Yeah. Matlab region, so the equation doesn't really encompass the region. The equation is for the condition in which you have to accept the token. So if the small model predicts a token xi, then in order to validate whether xi is a valid token or not, you would take the probability assigned to xi by the small model divided by the probability assigned to xi by the larger model, and you will see if that is less than or equal to 1, and that means that that is the best model to that is the best output.
What if, so just give an example, let's say the token is revolves. Uh, the larger model did assign higher probability to revolve than the smaller model did, but it also assigned even a higher probability to some other token. In that case, the larger model is saying that if we are not doing proper sampling, the larger model is saying that this is what we should.
Right. So okay, so the question here is that what if the larger model assigns a probability, a higher probabilities to some other token, but the token that we have sampled also follows this rule. So that means we would be accepting that token and we would not be looking at the token that is which should be the actual token that we look at, right?
Should we not?
Okay, so that is a really good question actually. Now this completely depends on how you sample from your smaller model. This is also a limitation because let's say that the token, it completely depends on how you sample from the smaller model. So if you're doing max sampling and the token which the larger model assigns a higher probability has a significantly lower probability in the smaller model, you will not sample it in the first place. But then again, so this algorithm in explains a concept. So you can, there are cases which you can sort of implement yourself. Like when you are implementing the algorithm, you can make certain changes to make it to make it more robust.
Right. So, but the problem is that we only do the larger model triggering once. So it won't give me the probability of the other tokens for the third place, right?
No, it will. So at every step, the hidden state outputs are actually
Okay,
probabilities. Yeah, so you have your probability distribution at each step. So given an input, you can also get like the larger model. Let's say, let's go back to that. Uh, Okay, so let's say the larger model actually predicted instead of revolves, it predicted rotates, right? So that means that if it is seeing Earth as the previous token, then for the next token, even if it's a hidden state, in your probability distribution, revolves would have a lower probability than compared to rotates. But then the smaller model itself has predicted only revolves, right? So we cannot, at that point in time, we cannot do anything without any prior knowledge. But if you want to do that, you can make that updates in your larger model, and we will talk about like how to pick a small model in the next few slides. One thing, shouldn't put too many animations. Okay. Okay, so is this point clear to everyone in the audience? I feel that a lot of you might be confused, like what is going on. I see only a couple of thumbs ups. So if you have any doubt, please ask. And please don't say कि शुरू से सब फिर से बताओ because we are pretty
So I had a
yeah,
query here.
yeah, please go ahead.
So here we understand that for the first time, when we are doubtful about a particular token, we can query it using both larger LLM and smaller LLM. But how do we decide that we have to query for that particular token?
Okay, so we what we do is we are not really querying the large LLM. We generate some lambda number of tokens from the small LLM, and then we feed that as the input to the large LLM. The large LLM will tell us whether these inputs are correct or not based on the hidden states that it generates. Uh, okay, so if you focus here, then you see that to my large model, I had fed three inputs. The earth revolves. It generates back the same inputs. The earth revolves, and it also generates around. So what it is doing is that it mirrors its inputs. But here's the interesting thing. For the input the large model has outputted earth. It is not really giving us a mirror. What it is doing is that it is predicting one step further than the input. So if the input was start token, the output was the. If the input was the output was earth. If the input was earth, the output was revolves. If the input was revolves, the output is around, right? So when you are predicting with the large model, you are getting, what you are actually getting is the next token that will be generated in the line. So 0 to n minus 1 inputs, 1 to n outputs. So 0 can be compared with 1, 1 can be compared with 2, 2 can be compared with 3, and n minus 1 here can be compared with n there. Does that make sense?
Yes.
Okay, so now what we do is, once we make, if this condition stands, that is the probability assigned to the token by to the sampled token by the small model is less than that of the large model, in that case we sample that token from the small model, that is we keep that token given this condition, otherwise we reject it and we accept the token that is actually predicted by the large model. Now in the actual paper, they don't really sample directly from the large model. They sample from an adjusted distribution. So what the adjusted distribution is, that you take this distribution which is p of x, you subtract q of x from it, you only keep the non-zero values and you normalize it, and then you sample from it. But just for simplicity sake, this is what this is what it is. Now to give you a better understanding of it, let's look at the algorithm. So you start with your small model MQ, your large model Q, MP. You start with a prefix and you start with your integer, which is lambda. So you start with lambda. Now, for a given number of, for a given lambda value, we want to generate tokens from the small model MQ. Now, if you look at the first line, we initialize an empty list Q. This will store all the subsequent probability distributions of all the decoded tokens. So now we run the loop from 1 to lambda. We give the input, which is prefix, and then all the tokens that are decoded up to that point. So when you start this list, the list that is next to prefix will be empty. So in the first step, the the input to the small model will just be the prefix, and then it would give you a probability distribution given that prefix. Then you will keep on continuing this process until you have generated for all the lambda tokens. Next, we take the outputs of the small model, which is prefix plus all the lambda tokens, and we make a prediction from the large model. So this is your lambda plus first prediction. Now Once you have that, we can start verifying all the outputs of the small model. So as you can see here, we are storing two outputs. Now, if the probability of a given token as assigned by the small model is less than that of the large model, then we add it as a true output. Otherwise, we add the prediction of the large model in that place and we simply break out of the loop. And we repeat it until the entire input is decoded. Okay. Now, if you see this in this algorithm is actually in serial. So first you are generating all the lambda tokens, then you are validating it by the large model. We can actually also run it in parallel. Now what happens in parallel is that you start with both your models, small model and large model. The small model starts generating first token, second token, third token. Now let's say if lambda is fourth, so it generates the fourth token. At the same time, the large model starts validating these four tokens. Now by the time it is validating, the small model can continue to generate more tokens. And if the result of the validation is true, that means if we don't have to break, we can still continue. And then again, we validate with the large model once we have lambda number of tokens. Now let's say the validation fails. So what we do is that we halt the execution, we go back the number of tokens that we generated, and then we start execution again. So that is how it goes. Now the real question is, what is the effect of MQ on this entire thing? What if I take a good small model versus what if I take a bad small model? So if I take a good approximator, so if MQ is a good approximator of the large model, you see that the total number of misses in validation by the large model are really less. So that means what you really are doing is you're optimally operating at the, like ideally you are operating at the speed of the small model, right? Except for a couple of places where you might miss. But if if your small model is a bad approximator, you will be constantly moving back and forth between the small model and the large model, and that would invalidate all the potential speed gains that you will have. So now the bigger question, or the biggest question, is how many tokens can I actually generate without failing? So in a single run of the algorithm, right, the first run that we do, we generate a total lambda number of tokens. Now for each input to generate a given token, let's say beta is the probability of accepting the token. That means I generated a token. What is the probability that the large model will accept it? Let's say that probability is beta. Now for each token that is generated, for each lambda tokens that are generated by the small model, we would have different probabilities of accepting all of these tokens, right? So the first token will be accepted with the probability of beta 1. The second token would be accepted with the probability of beta 2. Similarly, the lambda token would be accepted with the probability of beta lambda. Now these cannot really differ that much, right? I mean, if a model is generating a token, all the tokens that are generated by the same model will have almost the same probability of getting accepted, right? So I can just take an average of all of these beta values, which is the expected value of beta, and I can call it alpha. Now alpha is the probability of accepting a token, and 1 minus alpha is the probability of rejecting a token. The question that I'm trying to answer is, how many tokens can we generate without failing? So let's say if k is the number of tokens I can generate without failing. What happens when k is equal to 2? So I generate 3 tokens, t1, t2, t3. I accept the first one, I accept the second one, I reject the third one. So that means I generated 2 tokens without failing. If I have to write it in terms of probability, what is the probability of generating 2 tokens without failing? That is basically alpha multiplied by 1 minus alpha. That is alpha square into 1 minus alpha. If I have to do this for k equal to 3, that is generating 3 tokens without failing, it would be alpha cube into 1 minus alpha. If I have to check for lambda tokens without failing, it would be alpha to the power into 1 minus alpha. Now, if you know, this is a geometric distribution where you have So how to model this simply using a geometric distribution is that I am rolling a dice. What is the probability that I will get 6 after 5 rolls of dice? So the probability of getting 6 in one roll of dice is 1 over 6, and sorry, so the probability of not getting 6 in one roll of dice is 5 by 6. So I have to not get 6 for the first 5 times and then get 6 on the 6th time. So 5 by 6 multiplied by power 5 into 1 by 6. Now, if this is a geometric distribution, I can calculate the expected value of the random variable, which tells me the total number of, so I can calculate the expected value of k. Now what is k? K is simply the number of tokens generated without failing. If you simplify the above equation, you get this expected value, which is 1 minus alpha to the power lambda plus 1 divided by 1 minus alpha. Now, for those who are keen on mathematics, you might be asking why the limits of the summation go from 1 to alpha plus 1. Because if you see, if the model generates all the accepts all the tokens that we have, then we have lambda tokens from the small model plus one additional token that is generated by the large model. Now, this is a chart that was presented in the original paper, and this tells us what is the effect of lambda and what is the effect of alpha, that is probability of a token getting accepted. You can also consider alpha to be like an estimate of the small model. How good is the small model? So if you take a really bad model, which is you don't really get any gains because you're not, the accepted number of tokens is really less. But if you take a really good model, which is, let's say, with a acceptance rate of 80-85%, in that case you'll see that the expected number of tokens that you generate goes as high as 6 or even like 8 9 in certain cases. So this shows a relation between how good a model can be, and given that a model is good, what are the tokens it can, what are the number of tokens that it can generate per iteration. Now this is all good, this is all theory, but what we want to see is where people are actually using it. So OpenAI released this feature called predicted outputs recently. They use speculative decoding as a technique in predicted outputs. If you have used Cursor, the Cursor IDE, they had released a blog called Near Instant Full File Edits that also uses speculative decoding. Unfortunately, they took down the blog because certain people pointed out that their implementation was buggy and it was not working. Now the question is, what is so this is the base of speculative decoding. Whatever I have talked about is from the first paper on speculative decoding that came way back in 2002. Now things are changing. The most sort of latest advancement or the most accepted advancement in this space of speculative decoding is the Medusa architecture. Now what Medusa architecture says is that instead of having just one MLP head at the decoder end, you have multiple MLP heads at the decoder, and each of these Medusa heads will act as a speculator, and output of each speculator head can be given as an input to the model itself to verify in the next stage. What this does is that it removes the need for a smaller guessing model. So the biggest problem with speculative decoding is that if you don't have a good guessing model, then you don't really get any speed gains. And this is what Medusa solves by having the same model as the speculator and the same model as the verifier. Okay, so this is it um, uh, for the talk part. Now we will do some, like, we'll do an example. Okay, there is a question by Tushar. Yeah, please ask.
If you are using same model, how do you get speed improvement?
Sorry.
So if you use same model uh, to generate and to verify,
Yeah.
how do you get a speed improvement?
Okay. So the idea is that you don't generate just one output. You generate you generate a lambda number of outputs in one run. So the idea is, in one run, if I can generate multiple outputs, then I don't really have to do as many runs. When you generate auto regressively, you generate only one output token at a time. That is what slows it down. But if I can generate 5 tokens in one run, that means I am speeding up.
Okay.
Yeah.
And if let's say you generated 5 tokens and uh, during verification, second token failed, do
Mhm.
you keep remaining three or you discard all four and just keep the first one?
Yeah, so so whenever verification fails, we discard the token at which the verification failed, and all the
Hmm.
tokens
Right.
that succeeded that token. So if you generate 5 tokens and the third one failed, so you would reject third, fourth, and fifth, and now you would take the actual output that was predicted by the large model.
Okay,
And
thanks.
similarly
Yeah.
goes for Medusa. However, the way in which Medusa rejects is different to how we do it in traditional speculative decoding. Yeah.
Yeah. Okay.
Again, the lemma in this case, is there an analysis like if you replace a smaller model with this model itself, is there an ideal lambda, and does that really change with models? Because the alpha value would then be somewhere like it's always 0.9 around.
Yeah, so that is true. So you cannot, so like lambda cannot be infinite, right? I mean, I cannot just go and decode as many tokens as I like. But specifically in the case of Medusa, I am not sure, and we'll have to look at the numbers and kind of experiments that they did with it. Yeah. If there are any more questions, you can ask. Otherwise, I'll show you a short demo of speculative decoding. Let's suppose, Piyush, you can use your mic.
Yeah, I put an example. So let's suppose the smaller model says that we have a simple prompt that which are the planets that revolves around the sun, and the smaller model says that the planet Earth revolves around the sun,
Yeah.
while the larger model says that all the 8 planets revolves around the sun. So will speculative decoding help here?
Yeah,
And
so yes, so it will help. So what will happen is, if you look at the example that you have provided, uh, when if the larger model in that case would predict, let's say, the larger model predicted Mercury, but the smaller model predicted Earth. That means it will fail that condition,
yeah,
the QI by PI condition. So in that case, what will happen is, now the small model in its next step will start decoding from Mercury instead of decoding from Earth.
okay, but like how many replacement do we have here? Like because the token numbers are greater in output.
So it is like, we cannot, this cannot be determined like how many times it can replace. What we can only say is that given how good an estimator a model is, how many tokens will it generate in just one single pass, right? And also determining how good, like how good is the model, you will have to do some kind of an empirical measurement of that. So you take the small model as a speculator, you run it on the same corpus as you run it on some corpus, and you see how good or how bad is it doing. So you can only say, like you can only make that claim after that.
Okay.
You cannot really
So
determine that given 2 inputs, how many times will the first model fail.
okay.
There could be
So
a case, yeah.
I got it. So in theory, if a larger model wants to replace a single token with multiple token, it can happen.
A single token with multiple tokens? Sorry, I don't understand that.
So here we are replacing Earth with like 8 tokens. So this speculative decoding can do it, right? Or
No,
not?
so it's not really Earth with 8 tokens. It's actually Earth with Mercury, and then you will put that smaller input, which is the planet's Mercury. Then you will again give it to the small model and ask it to generate lambda tokens.
Okay.
So then the small model may generate Mercury, Venus, Earth, Mars, all the 8 planets, or how many lambda you have given. It may generate the correct outputs after the first break, or it may not generate them. It can continue to keep generating incorrect tokens.
Okay. Got it.
Fair enough.
Yeah. Thanks.
Yeah. So what we have as input is the definition of photosynthesis in English, and this has to be generated in German. it has to be translated in German. Now I have already ran it once through the small model. The small model translates it in 25 seconds. Of course, it is easy. It's an easy task for the small model, and the large model translates it in 77 seconds. Now we will do it speculatively. So it starts translating. So if you see the red token is actually the token that was generated by the small model but rejected by the large model. And then the green token is the replacement that was suggested by the large model. So again, we have one more token somewhere in the future that was rejected, and it will continue to generate. So if you don't see any red or green, that means that the large model has accepted all the tokens. So far so good. Again, one rejection by the large model. So if you see in terms of time, it took only 55 seconds, whereas the larger model took 77 seconds. The smaller model, of course, took only 25 seconds. So this represents that we have significantly sped up the generation using this particular approach. So that marks the end of this seminar. Yeah, so I think we can end it here.